gap between biomechanical research and clinical application.
Region-based vortex measures are commonly used to extract vortices. The ideal threshold to extract the vortex boundary, however, varies spatially. To detect vortices without manual thresholding, we utilize supervised deep learning. For the regression, we evaluate 3 recent network architectures. The resulting networks are able to detect vortices that grow in size due to diffusion, despite their angular momentum becoming smaller.
How do user interactions lead to insights? We present a case study with a tool that supports 5 types of interactions for exploring drug-target relations. Through an evaluation, we collected interaction trails, manually extracted interaction patterns, characterized the user insights, and explored the relations between interactions and insights.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Different sampling strategies have different performances in preserving features, but which one is the best? In this paper, we selected 7 sampling strategies along with 8 representative datasets and 3 important visual factors. We formulated 4 hypotheses and conducted a user study with 100 participants. For the derived insights, please refer to our paper.
We propose a multi-perspective simultaneous embedding (MPSE) algorithm for visualizing high-dimensional data based on multiple pairwise distances between the data points. MPSE computes positions for the points in 3D and provides different views into the data by means of 2D projections that preserve each of the given distance matrices. MPSE works on abstract data as well as graphs.
VIS has been successfully helping not only experts but also people who want to learn about AI. At VAST 2018, we presented GANLab, an interactive tool for learning about a deep learning model called GAN. But how does VIS help these learners? We conducted 2 evaluation studies, including log analysis of our demo used by over 100,000 people. We will be sharing our findings with you.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Given a dimensionality reduction scatterplot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
Many sampling strategies pay little attention to the preservation of significant contextual structures. In its paper, we propose a context-aware graph sampling method in a vectorized space to preserve not only contextual structures but also significant topological features. Welcome to pay attention to our paper. Its ID is 1259.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Being able to perform visual analysis on sensitive data in a privacy-preserving way has become more and more important. In this work, we look at two major research questions in differentially private data visualization towards better understanding of the relationship between the privacy parameter, visualization type, the analytic tasks, and users' performance through cross-source, user study, and simulated comparisons.
What do you believe is the correlation between labor union participation and corporate profits of different companies? How would you update your belief after seeing this scatter plot? In this study, we use a new elicitation technique to understand how people update their beliefs about correlations after seeing different visualizations with and without uncertainty depictions.
Good afternoon and welcome to the Topology and Scalar Field session. We have a lineup of 6 papers this afternoon, and rather than bore you with telling you all the details of them, I will simply say that the first one we're seeing, Julien and Tierny will be presenting, and it's TopoMap, a zero-dimensional homology preserving projection of high-dimensional data.
Hi everyone, my name is Julien Tierny. I am a research scientist with the French Center for Scientific Research, and I'll be presenting our work on TopoMap on behalf of Harish. So in many data-centric applications, it can be very useful to project complex data sets given as a high-dimensional point cloud down to lower dimensional spaces for the purpose of interactive visualization and exploration. For this, many techniques have been introduced in the past, and here we refer you to our paper and to a reference survey for more details. But generally speaking, most existing techniques aim so far at preserving some geometrical information during the projection, such as the relative distances between the input points. However, important information in the data can be encoded with different channels than the strict geometry of the point cloud. In several applications, the actual structure of the space sampled by the point cloud can be of first importance. And this motivates the definition of projection techniques capable of taking the intrinsic topology of the data into account. In that line of thought, a recent work by Jan et al. Built upon the landmark isomap approach, and specifically in order to preserve the Hwan cycles in the data, representative points from detected cycles are used as landmarks, and isomap is then used to project the data in a way that respects the landmarks constraints as much as possible. UMAP is another projection which has been very popular lately. It makes use of category theory to preserve neighborhood properties and produces projections that are similar to these of TSNE. In the scientific visualization community, there's topological landscapes, which visualizes the data as terrain, either in 2D or 3D, such that the terrain is the same contour tree as that of the original data. And however, note that while the generated terrains preserve the topology, the projected points themselves are not guaranteed to preserve the topology of the input. So different from these, our goal in this work is to preserve the persistence diagram of the connected components, technically the zero cycles, obtained through the RIPS filtration of the input data. So for this, let's first consider an example with 6 points in 3D. The RIPS filtration will start by growing balls of increasing radius around these points. Initially, it's the set of points themselves. As the radius grows, the balls start merging with each other, and here the two closest ones merge within a single component with this edge. So the edge added at this point in the filtration is responsible of the merge. This process continues, and here you have one more merge, and another here, and another there. And finally, in the end, we have only one connected component covering the entire input point cloud. So essentially, in the RIPS filtration, we start with endpoints, each of which is a connected component. And as the balls grow, connected components are destroyed by merging with existing ones until there's only one component left. So our goal is to project the points in 2D such that there is a one-to-one mapping between the components tracked by the RIPS filtration in the input points and that of the RIPS filtration of the projected points. So formally, this also results in the preservation of a topological object called the persistence diagram. So the key insight that enables this is the equivalence between the edges in the filtration that causes the merges, those topology changing edges, and the edges of the minimum spanning tree, or MST, computed using the Euclidean distance. This equivalence is further discussed in the paper, and we make use of it to project the points such that the MST edges between the components are maintained. So we do this in 2 steps. In the first step, we compute the Euclidean distance minimum spanning tree, the MST. In the second step, we iteratively build the projection by processing each edge of the MST one by one in increasing order of their length. So consider again the 6 points in 3D. Initially, each of these points form a single component in the projected space, and we then process the smallest MST edge. This merges the points P1 and P2. So to place them in 2D, this is simple. We simply place the points at a distance equal to the length of the edge. The next edge is then processed. And again, it is merging 2 points. The placement is again simple, and we now have 4 connected components at this point. And the next edge merged a 2-point component with a single point. So here we place it such that 3 points form a right angle triangle with the new edge lengths here being equal to the length of the MST edge being processed. So the next edge again processes a 2-point component and a single point. So we do the same process, and we at this point have only 2 components remaining. So the final edge merges these 2 connected components. And here the general procedure to process that is a little more involved. So first we take one of the connected components and we compute the convex hull of this component, and we rotate it such that the topmost edge is parallel to the x-axis. Next we take the other component, and again we compute the convex hull, and now we rotate it such that the bottommost edge is parallel to the x-axis. And now that we have aligned these 2 components appropriately, we place them in 2D such that the distance between the 2 convex hulls exactly coincides with the length of the current edge in the minimum spanning tree. And this distance is represented right here. So the idea here is that we want to make sure that the points in this convex hull and this connected component are at a distance in 2D that is exactly equal to the length of this edge in the minimum spanning tree from the points in this component. So with this, we obtain the projection of our 6 points in 2D, for which the length of the topology changing edges have been preserved constructively. And it's not difficult to prove the correctness of this procedure, and we refer you to the paper for more details. So while the previous process created a topology preserving projection, it is possible to add more customizations while still preserving the topology. For example, we might want to make the projection as compact as possible by minimizing the sum of the distances between the pairs of points, while still satisfying the MST requirements. We can frame this as a mixed integer nonlinear optimization, but typically this is difficult to solve. So we simplify the conditions, and specifically given 2 connected components, we can restrict the placement with respect to one edge of the convex hull. While this would still require nonlinear optimization, this formulation will not have integer variables, and we can therefore use standard solvers. In this example, consider the components C1 and C2. We want to place C2 at a distance d from the highlighted edge of the convex hull of C1. So once the optimization problem is solved, we then adjust the positions such that there exists exactly 2 points at the required distance. So now let's look at some results with synthetic data sets. And here each line represents a different synthetic data set with a specific topological structure. And here there's 1 color per connected component. And each column represents a projection method, and the rightmost column being the projection generated by our method, TopoMap. And here you can notice that TopoMap creates very characteristic star-shaped ensembles representing the data classes, with 1 star for each of the major connected components. So now let's look at some actual data sets collected from machine learning repositories. And these data sets are typically used usually to evaluate quantitatively the performance of classification algorithms. And here each color corresponds to a distinct class in the input data. For instance, for the MFET data set at the bottom here, each label, each color represents a number in the problem of automatically recognizing handwritten digits. And again, the star-shaped ensembles can be observed with the projections generated by TopoMap. So as further discussed in the paper, there is an equivalence between the components formed by the Rips filtration and the clusters identified by hierarchical clustering with the single linkage criterion. Thus, the centers of the star patterns computed by TopoMap actually correspond to the clusters found by hierarchical clustering. And this is clearly visible for the MFET example, where each cluster is represented by a distinct star center, here and there. So then, when interpreting the projections computed by TopoMap, the users should focus on the centers of the stars, which correspond to clusters, while outliers and boundary between clusters would be located at the tips of the long branches. And as discussed before, by construction, the persistence diagram in the projected space is identical to the persistence diagram in the original space. In that sense, our projection is topology preserving. But note additionally that thanks to the equivalence with hierarchical clustering with single linkage criterion, the hierarchical clustering computed in the projected space will also be identical to the clustering computed in the original space. To further stress the star centers, we also use a density-based visualization to display the projection. And here, the low density regions in 2D are grayed out, as you can see here progressively on the branches. So now we'll show a couple of examples from the paper about how such a visualization with the TopoMap projection can be used for visual exploration of high-dimensional data. So given the equivalence with hierarchical clustering, TopoMap can be used to probe and better understand other projection approaches. And this data set has been obtained by combining several urban indicators from New York City, such as taxi transit data and weather data. And in particular, each point represents an hour interval at Times Square, living in multiple dimensions, including the number of taxi pickups, the average fare, the average distance, outdoor temperature, level of precipitation, wind speed, and so on. So for such data sets, some similarities can be observed between points taken in the same hour but on different days, and some correlation can be expected between the number of taxi rides and the actual weather. So in this example, we'll look at the 10 largest clusters at a particular hierarchy, and the corresponding points are highlighted in the TSNE-based projection in the same data. And here we can observe that the clusters identified by hierarchical clustering are actually split with the TSNE projection while they remain localized with TopoMap. And here a cyan cluster is split into 2 locations, and the red cluster is split into 3 locations. So depending on the data, TopoMap's layout also produces long branches, and these typically correspond to outliers as mentioned before. And in some scenarios, these branches can also be used to better understand the transitioning between the clusters. Other distance metrics can also be used to generate TopoMap's projection. In this case, the MST on the original data is computing with the appropriate distance. However, the Euclidean distance is still used on the projected space. So to conclude, we presented a projection approach that provably preserves the topology of those 0 cycles generated by the RIPS filtration of the input data, and we refer you to the paper for all the details. While we focus on the 2D projection, it would be interesting to extend the iterative algorithm to place points in 3D and analyze the utility of such a projection. At the same time, it will also be interesting to see if higher dimensional cycles can also be included in the projection. So we'd like to thank you for your attention, and we'd be happy to take questions.
Thank you very much for that talk, Julien. While I wait to see if there are any questions in the Discord channel, I'm afraid I'm going to ask you one myself. I noticed that it's based on having the distance correct between the convex hulls. Do you ever get cases where the vertices or the points you're trying to connect are deep within the convex hulls?
So that's a very, very interesting question. So to try to rephrase the question, basically, you're asking when the points at the extremity of the edge in high dimension are not located on the boundary of the convex hulls that we try to assemble together. Is that correct? So the trick, and actually it's mentioned in the paper, but in the presentation, maybe it was not stressed enough, is that we do not enforce a one-to-one mapping between the minimum spanning trees in high dimension and low dimension, but we make sure that the edges that connect components have exactly the same length. So in short, what it means is that if we have a edge in the minimum spanning tree between vertex A and B, what we need to do in 2D is not necessarily to connect it to A and B, but to the components that contain A and B. So basically, we identify the components for A and B, And then we look at the convex hull of those components, and then we put an edge between those convex hulls.
Okay, that makes a bit more sense. I noticed somebody's typing a message into the Discord channel, so I'll wait for a minute for that to come through.
But this is a very technical question and a very good remark.
Well, I do try. Wilson Marsilio Jr. was asking, can I analyze similarity between instances as well as techniques like TSNE or UMAP?
I'm not sure it's fully clear for me what similarity between instances mean in this context. If the person could elaborate a little bit, that would be fantastic.
I'm not seeing an elaboration. Oh, wait a minute, he's now typing.
In the meantime, maybe I can advertise the fact that there's a few implementations of TopoMap already available out there if you guys want to give it a try. Mm-hmm. There's, of course, the implementation of the main author of the work, Harish. Basically, this is available on GitHub, and I will post the link after in Discord. And there's also Rene Coutura, who told me that he implemented TopoMap as well in his Node.js.
So the question is now being clarified. I mean, to analyze how much a digit trait in MNIST is similar to another. Does that make more sense?
So digit trait to basically to compare some, to evaluate similarities between clusters, I guess. Well, I'm not sure if I understand clearly the question, so I'm not sure if I can give a good answer.
I suspect that that's going to be an involved question, which I would recommend that continues in the Discord and possibly moves offline later on.
Okay.
Okay.
But
so I think it's time to move on to the next talk. So thank you, Julien, for your talk.
Thank you very much.
The next talk, and I will wait until the technician lets me know that it's queued up. The next talk will be Localized Topological Simplification of Scalar Data, and I believe it will be presented by Jonas Lukasczyk.
Hi everyone, my name is Dr. Jonas Lukasczyk and I welcome you to this talk where I'm going to present a localized approach to topological simplification called LTS. LTS computes the exact same result as the current state-of-the-art simplification procedure implemented in the topology toolkit, but LTS is an order of magnitude faster as it utilizes shared memory parallelism and constrains computationally expensive procedures onto the subsets of the domain that actually need to be simplified. But before I get into the details of LTS, I want to motivate our work and recap our thought process that led us towards this approach. Over the last decades, scalar field topology has been established as a Swiss Army knife for data analysis. Here you can see an example scalar field defined on a 2D surface where the scalar field corresponds to the height function. Scalar field topology provides various abstractions that can be used to characterize features in such datasets. For example, the critical points of the scalar field, contours for a given ISO value, sub and super level set components, the family of graph abstractions such as the merge tree, crown components of the merge tree, and of course the more small complex, here shown for the boundary of the surface. All these abstractions evolve around critical points, which play an essential role in many topology-based algorithms such as LTS. But datasets often exhibit noise, or there exists an importance hierarchy between features that can be used to filter features. Let's say by some arbitrary user-defined metric, the left maximum would be considered noise, so we want to filter any topological abstraction that is associated with it. So of course we can compute the abstractions as before and then post hoc determine which part of the abstractions belong to that discarded maximum and then remove them. So we would have to remove the left contour, super level set component, merge tree arc, crown component, and we would have to merge more small complex cells. This requires a tailored algorithm for each abstraction, and care has to be taken that they are all consistent with each other. LTS follows another approach where we actually change the input function such that it no longer exhibits undesired extrema. then any abstraction computed on the simplified field is automatically consistent, and on top of that we can actually do the simplification symbolically, but more about that later. There exist several approaches that follow this concept, and I refer you to the related work section of our paper for a thorough discussion of these approaches. For the sake of simplicity, it suffices to say that LTS is based on the approach of Tierny and Pascucci, who described generalized topological simplification of scalar fields on surfaces. Their approach is the default simplification mechanism in the topology toolkit, and we compare our results to this state-of-the-art implementation. However, their approach needs to iteratively process the entire scalar field to yield a simplification, and therefore often corresponds to the most time-consuming part of a topological data analysis pipeline. In the following, I will show how we can derive a localized simplification scheme that only processes the parts of the input field that actually needs to be simplified, and how we can even parallelize this process. Alright, so how does LTS work? I will explain this now from the perspective of removing maxima, but the case of removing minima is symmetrical. First, we need to determine the region that is associated with an undesired maximum. We can do this with a so-called superlevel set propagation, which starts at an undesired maximum and then always absorbs the largest neighbor of the region until the procedure encounters a vertex that has a larger neighbor that has not been visited by the propagation. Such a vertex must correspond to a saddle, so we have determined the complete superlevel set component. Next, we set all values of the region to the saddle value, which creates a scalar plateau. Now we could call it a day, but many topological abstractions require combinatorial robustness. That means a global, non-ambiguous vertex order. This leads us to the gold nugget of LTS, in which we determine a symbolic perturbation for which the plateau does not contain any critical points. This process can be imagined as fixing the plateau at the saddle and then slightly tilting it downwards. Technically, we want to derive a new scalar field on the plateau such that the saddle is the only maximum and every minimum exhibits a neighbor outside the plateau. Imagine if this would be true, then the saddle becomes a regular vertex since it must have a larger neighbor outside the plateau. And also every minimum becomes a regular vertex because every neighbor outside the plateau has to be smaller than the plateau as it was computed based on a superlevel set propagation. So extrema of the plateau become regular vertices on the entire domain, which is exactly what we want. The key insight to observe here is that enforcing these criteria is itself a topological simplification problem restricted to the plateau. Solving this local problem in arbitrary dimensions is very technical and you can find the details in the paper, but LTS essentially follows the iterative procedure defined by Tierny and Pascucci to solve this local simplification problem. On my webpage you can also find some additional slides that animate this procedure in detail for a more complex example. Now that we know how LTS works in general, I want to highlight that all these steps can be parallelized with some light synchronization. If we want to remove multiple maxima, then we can just concurrently compute the corresponding components, flatten their regions, and then independently disambiguate the resulting plateaus. In the case where multiple superlevel set propagations reach the same saddle, then we need to continue the propagation until we find a saddle with an unvisited larger neighbor. This is the case which requires some light synchronization at the saddles. Then we can flatten and disambiguate the combined regions at once. LTS can also be specialized for the case of persistence-driven simplification. As explained before, LTS can remove extrema based on any user-defined metric. If this metric corresponds to persistence, then in the previous TTK workflow one had to first compute all persistence pairs and then feed a blacklist of extrema that correspond to non-persistent pairs into the simplification procedure. However, superlevel set propagations used in LTS can actually be used to compute the non-persistent pairs without prior knowledge. So for this, LTS initializes for each maximum a superlevel set propagation as described before, but with the additional constraint that the propagation terminates as soon as it exceeds a given persistence threshold. After all propagations terminate, we know which propagations did not exceed the persistence threshold and therefore need to be simplified. This early escape provides a significant speedup over the previous approach, as we do not have to compute all persistence pairs in the pre-processing step. Now I want to give you a quick tour of some results we obtained with our C++ LTS implementation, which uses OpenMP for parallelization and which is embedded as a module in the topology toolkit. All our experiments were conducted on a machine with 12 cores, with publicly available datasets from different research domains. In the first case study, we characterized vortices in a computational fluid dynamics simulation that models the injection of a jet into a medium at rest. Here we can identify vortices via the ground components of the merge tree, in other words, the augmented leaf arcs of the merge tree. The initial vortex characterization shown on the left is broken up into small components due to noise. Usually one would filter extrema by persistence to join vortices into more sensible connected regions. But in this example, a single global persistence threshold is not enough to adequately portray the flow behavior. To generate the image on the right, we actually use different persistence thresholds for 3 different parts of the domain. At the bottom, we use a low persistence threshold in order not to discard the vortices, which would be lost for the more aggressive threshold used at the top of the jet. At the base of the jet, we actually suppressed all maxima except one, so now they are all segmented as one component. This highlights that LTS can handle arbitrary extrema selections, and that we can also use LTS for interactive analysis, since on a machine with 12 cores it only takes 7 seconds to simplify the field, whereas the state-of-the-art approach in TTK takes almost 3 minutes. Imagine the impact on your workflow if you need to adjust the persistence threshold. This is where LTS really shines. In the next example, we characterize the boundaries and nuclei of plant cells via contours, superlevel set components, and separatrices of the more small complex. If we use this feature characterization on the unsimplified input image, we end up with a lot of false positives due to noise. In this example, it makes sense to suppress non-persistent maxima saddle pairs, and to determine sensible persistence thresholds, we can examine the persistence curve if it exhibits any plateaus. The endpoints of such plateaus often correspond to thresholds that separate noise from signal, and we can see that the threshold on the right side of the plateau yields some strong segmentation results. This example also highlights the primary advantage of pre-simplifying the data over post-simplifying the abstractions, namely that once the data is simplified, all subsequent computed abstractions benefit from the simplification and are consistent with each other. In the silicium dataset, we used the more small complex to represent the structure of the silicium grid. This example highlights that LTS only affects regions that actually need to be simplified. As shown here, filtering extrema that do not correspond to silicium atoms only affect the feature characterization locally. In the backpack dataset, individual items can be identified via contours, but the persistence curve does not exhibit a clear plateau, so the user has to experiment with different persistence thresholds to produce an adequate segmentation. As mentioned before, the significant speedup of LTS enables such iterative analysis. The bold numbers in this table indicate the speedup of LTS over the baseline approach of Tierny and Pascucci. LTS is across the board significantly faster than the baseline approach. Even the non-parallel version of LTS is faster, as it only processes the parts of the domain that actually need to be simplified. In parallel with 12 cores, LTS is at least 20 times faster and achieves an excellent parallel efficiency. For stress cases where we only want to simplify all but one extremum, performance starts to deteriorate, as LTS now has to process almost the entire domain. But LTS is still up to an order of magnitude faster. In conclusion, we proposed a novel approach to topological simplification that is output sensitive, restricts computationally expensive procedures onto parts of the domain that actually need to be simplified, and that can additionally be parallelized. The resulting speedup of up to an order of magnitude enables interactive analysis, and the presented approach is going to be released through TTK. However, the current LTS implementation is optimized for desktop machines, so it is likely that LTS needs to be adapted to fully leverage the computational power of an HPC environment. As a technical limitation, LTS is only able to remove extrema saddle pairs. So in future work, we need to explore if LTS can be extended to also remove saddle pairs. This concludes my talk, and I thank you all for your attention. Goodbye.
Thank you, Jonas, for that excellent talk. While we wait to see if there are questions on Discord channel, it falls to me to see if I can come up with something tricky for you. And I'm actually quite interested in the question of what happens if you have a nested structure where you have an inverted sublevel component hidden inside your superlevel component.
Yes, so an easy example for this case is if you would imagine a 1D curve, right, where you have the height function on top, and somewhere on this curve you have this M structure, basically. And then you want to remove the two maxima, and there are two minima in that part you are now going to simplify, right? So this is now more of a philosophical question, like how a simplification of such a structure would look like. What LTS would do, it would just pull these maxima down to the contained minimas.
In other words, what you'd do is you would simultaneously flatten both peaks, but that would actually be an extremum cancellation.
Yes, and then we can continue to, if we wanted to remove that entire M structure. Basically discarding those minima we might want to have preserved, but we can later symbolically introduce them again.
Yeah, the question actually gets more interesting in 2 and 3D, and in 3D in particular, you get structures like nested spherical shells, and that's an interesting stress test.
Yes, yes. So we ran this on a lot of data sets, and since we have this procedure that basically processes these maxima components where you often hit saddles, where you now need to join regions and stuff. Theoretically, this is a real stress case for our implementation, but the algorithm is already designed in a very efficient way with Fibonacci heaps actually to organize the sweep fronts and the collected sets we compute on the fly pretty efficiently. So even if you have to do a lot of these join events, actually the algorithm is still linear logarithmic.
Okay. Yeah. I suspect there's a productive conversation on that offline. In the meantime, we've got a couple of questions showed up. The first is from Peter Christoph, who I will point out is my PhD student, who's asking, do you need to specify which extrema should be simplified before running the algorithm? And if so, how are they chosen?
Yeah, so basically LTS would supports 2 ways to do this. The first way is where you, as the user, specify by some user-defined metric which extrema you want to remove. So actually, Hamish, you published a paper in biomedical imaging where you propose to remove extrema not based on persistence, but on, for example, some volume threshold on the corresponding contours. So you could use that metric, for example, to decide which extrema you want to remove, and then can just feed this into our algorithm. The other metric, which is often used, is persistence. And for persistence, you would not have to pre-select these extrema. There we can use this procedure where we just start to do propagations from every extremum, but do this early cancellation when we go deep into, also exceed the persistence threshold during a propagation.
There is a follow-up question to that, but there was another question asked first, so I'll do it in the order they're in the Discord. Anke Friederike was asking how well your algorithm strongly and or weakly scales.
Yeah, that's also a very, very interesting question, though I hinted at this a little bit in the future work section, because right now we just did these experiments on the desktop machine, and I have the suspicion, although I did not confirm this, that it right now not scale well if you suddenly use 50 cores or something to do this parallelization. So I don't have an exact answer on how this scaling would look like, but I think some modifications are necessary in order to get good scaling. But at least on desktop machines, it works well. Yeah.
Yeah, I hope that answers Anke's question. I might be able to help you shed some light on that in light of the work that we've been doing recently, but that I think really does need to be taken offline.
No, so, I'm happy to chat about that later,
yeah. So let's take Tushar Athawali's follow-up question, which is whether there are any guidelines on choosing threshold levels for local simplification or other parameters.
Well, so if your metric is persistence, then a standard way is to look at the persistence curve or the persistence diagram and check for plateaus to know basically for which persistence threshold suddenly a lot of features would disappear. Usually this is the threshold that indicates where you would get rid of noise. But this is always a dataset to dataset specific question, and you need to explore this interactively. But this is exactly why LTS is beneficial, because if you were experimenting with these stuff before, you probably had to wait a long time before you can see the impact on your feature characterization. But now stuff that took 3 minutes before now just takes 6 seconds. So you can at least explore this a little bit more efficiently. And if you have another metric to decide which extrema you want to look at, then it's obviously up to you as the user to decide what your threshold criterion are.
Right. I think in the interest of time, we'll now want to move on to the next talk. So once again, thank you very much, Jonas. That was a very interesting talk.
Yeah, thank you. All right.
So the next talk is on mode surfaces of symmetric tensor fields, topological analysis and seamless extraction, and I believe it's being presented by Botong Qu. So please, can we start that one?
Hi, this is Botong Qu from Oregon State University. Today I'm going to present our work on mode surface extraction with Lawrence Roy, Yue Zhang, and Eugene Zhang. First, I will give a brief introduction to our work to answer the following questions. What's the mode surface? Why is it important? Why is it hard to extract? As we know, 3D symmetric tensor field has wide applications such as medical, engineering, and science. Tensor field topology consists of degenerate tensors and neutral tensors. There are two types of degenerate tensors. Linear degenerate tensors, corresponding to uniaxial tension in solid mechanics. Planar degenerate tensors, corresponding to uniaxial compression. Degenerate tensors form curves in 3D. Neutral tensors correspond to pure shear in solid mechanics, and they form surfaces. Degenerate curves and neutral surfaces are special isosurfaces of the tensor mode function. More specifically, linear and planar degenerate curves correspond to mode 1 and mode -1 surfaces. Neutral surfaces are mode 0 surfaces. Given a mode value mu, since both the positive and negative mu satisfy the mode function, we always consider mode mu and mode negative mu surfaces together during the extraction. We refer them together as generalized mode mu surfaces. So how do the degenerate curves morph into neutral surfaces? How do these topology features interact with each other? All these questions can be answered by studying the mode surfaces. In this video, we show the morphing of the mode surfaces along with the changes of the mode values. We can see how different types of degenerate curves change into each other and how they transit into neutral surfaces. By visualizing this change of the mode surfaces, we can get an insight into the underlying physics, which cannot be observed from the degenerate curves and the neutral surfaces themselves. Besides, the mode surface itself can also reflect some interesting structure of the underlying physics. In this image, we can observe a hole on the bottom of the mode surfaces. Some differential properties, such as the normal and the principal curvature directions of the mode surfaces, can also be informative. To observe these properties, we need to have a robust and seamless extraction of the mode surfaces. There are some state-of-art methods to extract mode surfaces and neutral surfaces. For example, Palacio et al. Introduced to extract mode surfaces using A-patches method. However, since this method requires a subdivision of the mesh, it takes a long time and is hard to convert for high-degree polynomial. Also, the extracted mode surfaces can contain holes for different resolutions of the subdivision between adjacent tetrahedra. Roy et al. Proposed one method to extract neutral surfaces based on the parameterization. However, their method requires clipping of the extracted neutral surfaces against the faces of the tetrahedra. This can generate holes on the neutral surfaces between adjacent tetrahedra. Our work benefits from many fantastic previous works of the 3D tensor field analysis. We list them here for your reference. I will now start to talk about the analysis and algorithm we propose. When trying to compute the mode surfaces, We realized that since the high degree of the mode function, it is so hard to compute the mode surfaces directly. We wondered whether there is a space we can utilize to make it easy to parameterize the mode surfaces. After some study, we realized that the meeting eigenvectors of the tensors can be used to differentiate mode surfaces points. So we start to look at all possible meeting eigenvectors in a linear tensor field. This gives us the meeting eigenvector manifold. We visualize this manifold as a unit sphere. For each meeting eigenvector, a 2D asymmetric tensor field is defined with the equation shown on the screen. We refer the audience to our paper for more details about this equation. This asymmetric tensor field is visualized on the sphere with lake. For one meeting eigenvector and its corresponding mode surface point, when projecting the 3D tensor fields on the planes whose normal is the corresponding meeting eigenvector, the dominant eigenvector directions of the mode surface points match the eigenvector of the asymmetric tensor field. Each real eigenvector of the asymmetric tensor is used to map the meeting eigenvector to one mode surface point. So we can classify the meeting eigenvector manifold into two regions based on the asymmetric tensor's eigenvalues. The orange region is where the asymmetric tensor has two real eigenvalues. We call this region real domain. The gray region is where the asymmetric tensor has complex eigenvalues. We call this region complex domain. The transition between the real domain and complex domain is what we call complex domain boundary. We further classify the real domain into three regions based on how does a meeting eigenvector be mapped to mode surface points. A meeting eigenvector in the blue region corresponds to one point on the positive mode surfaces and one point on the negative mode surfaces. A meeting eigenvector in the cyan region corresponds to 2 points on the positive mode surfaces. A meeting eigenvector in the magenta region corresponds to 2 points on the negative mode surfaces. For two antipodal points on the meeting eigenvector manifold, their major eigenvector and minor eigenvector of the 2D asymmetric tensor field swap. In this image, we can see that the major eigenvector, which is colored as red, become the direction of the minor eigenvector of its antipodal point. This interesting property gives us a way to simplify the mapping. For each meeting eigenvector, we always pick the mode surface point, which is given by the major eigenvector of the asymmetric tensor field. In this way, we can map each meeting eigenvector inside the real domain to a single point on the mode surfaces. We provide a parameterization of the complex domain boundary. Note the asymmetric tensors of the two antipodal points on the boundaries have the same one eigenvector. So two antipodal points on the complex domain boundaries are mapped to the same one mode surface point. The asymmetric tensor field on the meeting eigenvector manifold keeps changing as the mode value changes, and it works for all mode values including mode 0. During the above animation, we can observe the number of complex domains changes. Two above domains merge into one complex domain at one specific mode value. The moment when two complex domains merge is called bifurcation. In our work, we find what the mode value would make this bifurcation happen. The topology of the mode surfaces change before and after the bifurcation. When there is only one complex domain boundary loop, the generalized mode surfaces are topologically a torus. When there are two boundary loops, the generalized mode surfaces are topologically a double torus. Our method has been adapted to extract neutral surfaces. It provides a unified framework to extract mode surfaces, degenerate curves, and neutral surfaces. We first find mode curves inside each face. Then we sample the mode surfaces inside each tetrahedron using parameterization. At last, we stage mode surfaces together from each tetrahedron across common faces. In the interest of time, we refer the audience to our paper for more details. Our method is robust. The results generated by our method contains fewer missing pieces. Also, we can get the neutral surfaces and the mode surfaces in a shorter time. The mode surfaces extracted by our method are seamless, which makes it possible to conduct further analysis on them. And the user can decide the sampling resolution to balance between the quality and the speed. We apply our method to several solid mechanics datasets to study the compressive behavior. These datasets are generated by using Abacus finite element analysis software. We create one block and apply a pushing load on one side of this block, and apply a pulling up load on the other side of this block. Under this setting, we find a very interesting symmetry on the extracted mode surfaces. When visualizing the principal curvature direction, we observe a sudden change of these directions in the middle part of the mode surfaces. This shows that the middle part of this surface is being pushed more in the length of the box than in the width of the box. This scenario is simulating a highway bridge where a truck parked on it. We observe an interesting wave at mode -0.53 surfaces. As the mode value changes to 0, the wave shape becomes smaller and ultimately disappears. More application analyses can be found in our paper. To sum up, in this work, we provide a new analysis of the mode surface topology. Based on this analysis, we provide the first approach to seamless extract mode surfaces. Our method is fast and robust, and we apply our visualization on several stress tensor fields to study the compressive behavior. In the future, we plan to study more about how could we sample the meeting eigenvector manifold to make the triangular mesh of the mode surfaces have higher quality. Also, we would like to adapt our method to other feature surfaces. We also want to extend tensor field analysis to more complex physical behaviors and explore more to better understand how do the patterns of the mode surfaces relate to the load configurations. We would like to thank the reviewers for their valuable suggestions. Also, we appreciate Kyle's help on video recordings. This work is partially supported by the National Science Foundation. Thank you for your watching.
Thank you, Botong, for that talk. I found it very interesting. And again, while we're waiting for people to contribute questions in the Discord channel, I will start off by asking a question of my own. You mentioned that your approach is robust. Are there any cases where it fails due to numerical problems in finding boundaries or curves?
Actually, to make the algorithm robust, when we are finding the curves on the faces, we have done a lot of work to handle different special cases. For example, when we are tracing, we need to adjust the step to make sure that we don't go outside of the triangle suddenly and make abstract turn on the face. So all these details actually are included in the paper, and we have done a lot of work to make this tracing part as robust as we can.
As robust as you can, but what I'm concerned about is that it's well understood that when you're tracing streamlines numerically, that they have a tendency to be worst behaved near the most topologically interesting points. So I would expect to see some sort of similar behavior. Have you seen any such behavior?
In our experiments, we haven't found such a case. Like I said, we found it at first, and we already solved all the special cases that we found. For the other cases, in the future's experiment, maybe we will find more. But I agree with you that the numerical tracing is very tricky. So I would expect that we will have some cases that would have the similar problem. And
so you're saying that you've resolved all the ones you've run into so far. You have resolved all of the problems you've run into so far.
Yes. And also there is another case that that's also we mentioned it in our future work. And in the future, we also noticed that this tracing part can be very tricky, and we would like to study how can we use the median eigenvector manifold to parameterize these phase intersections. If we can do that, then we can solve this numerical tracing problem like totally.
Okay, that sounds sensible. I do note, however, that we're now running a few minutes late, so I think we'll transition to the next talk. Thank you again.
Thank you.
The next talk will be delivered by Huan Liu, and it's entitled A Suggestive Interface for Untangling Mathematical Knots.
Hello everyone, my name is Huan Liu, a PhD student at the University of Louisville. I'm going to present our paper, A Suggestive Interface for Untangling Mathematical Knots. We developed a sketching interface where users can untangle complicated mathematical knots with system-generated suggestions. Here, I have a screen image of our interface. The upper left panel is a canvas to draw, edit, and deform knots with the right master moves. Our system can generate and display suggestions in the upper right panel to continue untangling knots. Our interface shows the key moment when critical changes occur during the knot deformation in the left bottom window to facilitate our understanding of mathematical knots. My presentation will have four main parts. I will first introduce the background of this visualization work, and then I will focus on the details of the implementation. I will present results from our preliminary usability test, and then we'll summarize this work at the end. Mathematical knots are one-dimensional streams embedded in three-dimensional space. In the topological field, two knots will be considered the same if we can deform one into the other without cutting or self-crossing. Like these two groups of knots, although they have very different visual shapes, we can deform the left ones into the right ones by performing some knot deformations. So, they are equal in topology. A fundamental problem for studying knot theories is how to untangle knots to have minimum crossings. We can perform the knot deformation based on three elementary changes called right master move. It's easy to understand these three types of moves. The first one is to twist and untwist a knot, and we call it R1. And the R2 is to move one loop over another. The third one, R3, is to move a stream over or under a crossing. A knot can be transformed to its topological equal knot by performing limited times of these three moves. Although the right master moves are easy to understand and apply, and they have already been proved that they can untangle any knot. The challenge is how to select and decide the right sequence of right master moves to untangle knot fully. For example, like this one, it is so complicated so that it is almost impossible to untangle it manually through a very long sequence of moves. That's the motivation behind our paper. We want a suggestive interface that allows users to apply the right master move to the knot. If needed, our interface can do the calculation and provide suggestions whenever users need help to proceed further. And of course, it can ensure each move being applied is a legal right master move. Our primary design is, just like the diagram, to have an interface for one to draw and modify knots with system-generated suggestions whenever requested by the user. We have an analytical engine behind the visual interface, which generates Gauss code from the knot's geometric shape. and provides move suggestions by analyzing the Gauss code. When users attempt to apply a move, our system validates the move before it eventually changes the notch. Now, let's talk about some details. Our interface allows users to begin by creating knots. They can create knots by uploading a raster image or constructing a knot by sketching one in our view panel. When a raster image is uploaded, our system will construct the three-dimensional knot structure through image processing operations. The operations include cropping and resizing, grayscale converging, binary converging, thinning, crossing locating, and sampling. As illustrated in the pictures, we reconstructed a trefoil knot from a raster image from the Wikipedia website. Or, like this image, one can also draw a knot diagram in our sketching canvas. Once we have an initial knot, we can deform it by master moves or follow system-generated suggestions that rely on the analyzer that works behind the view interface. Here is the primary mechanism. First, the analyzer will parse the knot's geometric structure and turn it into Gauss code to denote its topological properties. Gauss code is a sequence of labels for the crossings. Each label repeats twice to indicate a walk along with the diagram from a given starting point and returns to that point. We treat two knots the same if they have the same Gauss code. Then, the analyzer works with the Gauss code and holds the corresponding relationship between the knot's geometric shape and its Gauss code. Before we talk about the analytical process, I need to introduce a concept, the view tangle. A view tangle is a knot region where our interface will highlight and guide the user to perform mathematical moves. It is a closed region of a knot where the knot crosses its area precisely 4 times. The purpose I introduce a view tangle is to generate two kinds of moves based on the red master move. We keep the first and the second type of red master moves, and design two kinds of generalized translation moves to replace the third one. We call them T1 and T2. As you can read from the diagram here, T1 is a translation move to remove the original crossing and create one on the opposite side of the tangle. T2 is to relocate the strand intersecting both tangle segments to the opposite side. Next, we will introduce a numerical method that can read the Gauss code from a knot and know how to untangle it based on the 4 basic moves. Here are more details. Figure A shows how to identify and perform R1. Look for two adjacent integers that negate each other. Once this condition is found, that means we found a R1. Remove these numbers when performing R1. The program will look for two adjacent crossings with the same sign, locating these integers negative and determine if they are adjacent. These are conditions of R2. The 4 integers will be removed after R2 is performed. In Figure C, the crossing immediately beyond the tangle has 2 crossing integers negative of each other to perform a T1. When performing a T1, we first negate the value of every number composing the tangle, flipping it over, and remove the 2 numbers composing the crossing adjacent to the tangle from their original position and inserted them to the opposite side. The condition of performing T2 is that the 2 crossings beyond the 2 adjacent ends of the tangle are both overpasses or underpasses. When performed at T2, keep all integers in the tangle's Gauss code and relocate adjacent integers beyond the tangle to the opposite side of it. Now, this is the entire analytical procedure. Our analyzer first reads the knot's Gauss code and saves each number's position information corresponding to its geometric shape. Then it identifies and performs R2. The next step is to identify and perform R1. If no R2 and R1 can be performed, it will look for all tangles with sizes greater than 0. After that, check if T1 or T2 can be applied to any identified tangles. For T1 and T2, besides the condition to perform moves, there is an extra condition. There should be R1 or R2 available for next untangle step after completing T1 or T2. If the analyzer finds available moves, it will propose suggestions by popping dialog window and highlighting where the user should edit. Now, editing a knot is simple. The user only needs to redraw the highlighted area follows the directions. We also provide another way for users to edit knots. Users can mark out where they want to edit. Once our system confirms that the area marked out meets the condition of red master move, users can redraw its part. The last step of the process is the move validation. When the user edits a knot follows suggestions, the program performs the virtual move on the Gauss code to get the virtual Gauss code. Once the user submits an edit, our system will read the Gauss code from the new knot and compare it with the virtual Gauss code. If they are equal in topology, the program will accept this edit, otherwise it will discard this change. We have performed a preliminary usability test to evaluate our suggestive interface. We invited 10 non-expert participants to perform 3 unknotting tasks with 3 complicated knots. To have comparison groups, we asked the user to use some other tools, the knot plot, and our earlier work, the Untpad. Knot plot provides a physical simulation method to untangle knots automatically. Notepad presents an interface to let users untangle knots by pure drawing, but there is no system suggestions. This table shows the result of our test. All participants can complete the task with knot plot and our suggestive interface. However, with Notepad, only one participant completes one job successfully. Another participant nearly completes a task. Other participants stopped working after an average of 8 minutes. Interviews with them revealed that it was almost impossible for them to untangle knots with complicated structures without system-generated suggestions. The user study shows a promising result. The system-generated suggestion can make it faster to untangle a knot and make it possible to untangle a complicated knot. All participants agree that our suggestive interface can help them to understand an essential theoretical result by interaction with the knot step by step. Therefore, they gave the highest numerical rating to our interface on learnability. These results suggest the new knot interface is an improved interface that can enable and enrich one's mathematical experience on knots with complicated structures. Our interface approaches knots in a closed and most intuitive way to the mathematical problem compared to other approaches and interfaces. The user study has suggested that non-expert users can benefit from the interface to gain intuition. It can also help experts illustrate geometric structures and red master moves of knots to non-expert audience through graphics interaction. In the end, I want to thank the National Science Foundation for supporting our work.
Thank you for that talk, Juan. I must admit that I haven't been following Notplot for years, although I did know Rob Schrein when I was a PhD student. So perhaps you can clarify something for me. It seems to me that if you can make a suggestion, you ought to be able to untangle each of these knots automatically. Is that the case?
Yeah.
So if you can untangle the knot automatically, what exactly is the use case for this tool? Who do you envision using it?
Okay. Um, our target user is some people who interested in knot theories, but they are beginner, so it is hard for them to understand the right method move. And for a complicated knot, although we have the tool that is called a right method move, for beginners, it is they usually cannot deform it by using the right method move. So our tool can help them to understand how the right method moves untangle a knot, and we also can use this tool to help the expert to illustrate how to untangle knot to non-expert audience.
Okay. Related to that, the next question is, are there unsolved problems in knot theory where a tool like this would help the expert understand what comes next?
Okay. The most improvement of our work is that can untangle complicated structures of knot, and when on each changes we extract the critical moment and can extract a series of some consequence of images that can show each step for untangle a complicated structure of knot to the simplest geometry shape, and by using this tool, we can for the expert we can compare if the two knot with very different and very complex structure have the same topological property.
Mm-hmm.
Yeah, that's it.
So there's a question in the Discord. Peter Christoph is asking whether this tool can also be generalized to links.
Yeah. In fact, when we construct a link, we have a tool that uses simulation method. Just so we can perform a simulation physical force to the link, and that can help the software to divide the two link and separated it, and we can untangle each one, and finally we can untangle both.
Okay, I think that answers the question. We are now, I think, about 8 minutes late, so I shall move on to the next talk, if I may. So thank you again. That was a very interesting talk. The next talk will be presented by Jiayi Xu, and it's titled Geometry-Driven Detection, Tracking, and Visual Analysis of Viscous and Gravitational Fingers.
Hello everyone, my name is Jiayi Xu. I'm glad to present our work entitled Geometry-Driven Detection, Tracking, and Visual Analysis of Viscous and Gravitational Fingers. My co-authors are Shumo Data, Wenbin He, Joachim Morgate, and Han-Wei. We are from the Ohio State University. In this work, we study viscous and gravitational fingering phenomena. For example, when pouring honey into water or making a lava lamp, the viscosity or density contrast between fluids causes viscous and gravitational flow instabilities and results in finger-like features. The time-varying data in this work are generated from a simulation of carbon dioxide storage, and is applied for global warming mitigation in earth science. In the simulation, CO2 is injected from the top of a rectilinear aquifer. CO2 volume tends to spread out from high-density regions to low-density regions. Hence, high-density regions usually form the center of the finger structures. The simulation finally outputs the time-varying volumetric data for CO2 density over the entire aquifer domain. We interviewed Earth scientists for their analysis requirements. They were interested in spatial temporal exploration of fingers. For the spatial exploration, they wanted to identify fingers and branches in space automatically. Also, it was important to extract the connections between branches. The connectivity of branches might help them develop new scaling laws for the analysis of flow instabilities. For the temporal exploration, scientists were interested in the formation and evolution of fingers and branches. They wanted to identify the growth, merging, and splitting events of the time-varying fingers. In the following, we presented the details of geometry-driven solutions for the spatial temporal exploration of viscous and gravitational fingers. We first present how to detect fingers and branches automatically in space. The viscous and gravitational fingers are ill-defined in the literature. A science paper in 2018 reported that the finger feature is hard to define, but if you see it, you recognize it immediately. Previous works usually use the density thresholding to extract fingers. With a specified density threshold, the regions with density values larger than the threshold are extracted. Although the density thresholding is efficient, it is not sufficient to extract complete branches. For example, here is a finger that contains high-density branches and low-density branches. Also, the high-density branches are connected by low-density regions. If we use a high threshold, although the high-density branches are separated, the low-density branches are missing. If we use a low threshold, the low-density branches are preserved, but the high-density branches cannot be segmented. We propose a ridge-guided finger detection. Ridges originally are structures of surface topography. For example, in this picture, they are the mountain's sharp crusts. Then the mathematical properties of ridges were studied. Ridges of a smooth function are a set of curves or surfaces whose points are local maxima of the function in certain dimensions. In computer vision, ridge detection is used to detect human fingers in 2D images. For example, we can detect the ridge-like curves from the terrain defined by pixel intensities to extract human fingers. Since viscous and gravitational finger structures are local high-density regions in 3D space, we propose a 3D ridge-based detection for the fingers. Rather than detecting ridge lines, we detect ridge fossils, namely the fossils containing ridges. The ridge fossils produce more robust features and capture the branching structures of fingers well. Ridge points are local features that satisfy two ridge criteria. The first ridge criterion constrains the directional derivatives of density function, ensuring the detected points are extreme points. The second criterion requires two eigenvalues of the Hessian matrix defined at detected points, and constrains the two eigenvalues to be smaller than zeros, ensuring the detected extreme points are local maxima in 2 dimensions. Based on the ridge criteria, our ridge fossil detection consists of 2 steps. First, since the original density function in space is unknown, we approximate the density function. For each fossil, we establish a second-order Taylor polynomial based on neighboring fossils' values to approximate the density function near the fossil. The second-order Taylor polynomials can also provide local approximation of the density function's derivatives, including gradients, Hessian matrices, and the directional derivatives. We decompose the approximated Hessian matrix to estimate the eigenvectors and eigenvalues. In the second step, we compute ridge structures using the approximated derivatives and ridge criteria. Then we examine whether voxels contain the ridge structures to extract ridge voxels. Here we present the results of the ridge voxel detection. The first row shows the side view of the raw density volume. The second row shows the detected ridge voxels. The side view indicates that our method can extract both low density and high density branches and separate different branches. For the top view, ridge voxels can also capture the high density hexagonal cells in the domain's top layers. We dilate ridge voxels to recover connections between close branches. Until achieving the maximal connections of finger branches, we call these finger calls. We continue dilating the finger calls until achieving complete volume, enabling us to analyze whole fingers in space. We skeletonize the finger calls and can get the connections and height of finger branches. The skeletons can show geometric features of fingers and branches clearly. We then present visualization designs to check time-varying fingers and branches. To visualize the characteristics of finger branches, we draw geometric glyphs. For the side view, scientists are interested in the connections between branches. We apply planar visualization to draw branches as vertical lines and draw connections between branches as horizontal lines. For the top view, scientists are interested in the spatial distribution of branches. We draw branches as Voronoi cells, which can clearly show branches' positions and visualize the sizes of branches in space. Next, we embed the glyphs of finger branches into a tracking graph and create the geometric glyph augmented tracking graph to help track finger branches. In this tracking graph, each row contains fingers and branches at a time step. The temporal related fingers are connected through links. Colors represent 3 temporal events: orange for growth, green for splitting, and purple for merging. The thickness of links encodes sizes of overlapping volume between related fingers. Moreover, crossings between links are minimized to reduce the visual clutter. We further designed interactions for tracking branches, which are explained in case studies. We then present the case studies and the interactions by using our developed techniques. We constructed a visual analytics system consisting of 6 panels. The 5 panels in the top row are for the spatial exploration of fingers. The tracking graph in the bottom row is for the temporal exploration. The first panel is used to select a depth of interest. Then the second panel presents the density field slice of the selected depth. The projection panel shows the distribution of fingers in space by representing fingers using convex holes, and support the selection of interest fingers. After scientists select a finger, the finger volume and skeleton are shown in the 4th and 5th panel. The selected finger will also be highlighted in the tracking graph. 2 Earth scientists used our system to perform case studies of fingers. In the first spatial exploration case, scientists were interested in whether fingers tend to form along with boundaries of the top hexagonal cells or form below the centers of cells. The finger skeleton can facilitate scientists to answer this query quickly. By rotating the finger skeleton, scientists can quickly find that this finger grows along with the top cell's boundaries rather than forming below the cell's centers. The next case is for tracking branches using glyphs in the tracking graph. We highlight a finger with a merging and a splitting event. Scientists can hover over links to identify the temporal correspondence between branches after the merging and the splitting events. Here, this case shows how to track branch volume. A finger with a merging event is labeled. Finger A and finger B merges into finger C at the next time step. By clicking A, scientists identify A had 2 long branches and a short branch. The volume of C constrains the contains the branches from A and B. Scientists hypothesize the left volume of C comes from A. Then by clicking the link between A and C, the volume of C that comes from A was shown for branch volume analysis. In conclusion, we have two contributions. First, we propose a reversal-guided finger detection to facilitate the spatial exploration of fingers and branches. Second, we designed a geometric glyph augmented tracking graph to identify temporal events of fingers and track branch with interactions. Thank you for listening. We also thank our funding providers. I would like to take a few questions.
Thank you for that talk, Jai. It's always nice to see development over the years, and there's been considerable development on how we deal with fingers. Have you got any feedback from the scientists yet on whether it makes their task more efficient?
Yes, actually, when we developed the system, we worked with the scientists closely, and they usually give us valuable suggestions. For example, at first they suggested us to identify the geometric structures of the fingers, which is the main motivations of our work. Then after we have extract the fingers, we communicate with them to verify that the fingers we extracted satisfy their cognitions of the fingers, and they say, oh, that we extracted is actually what they want for the analysis. And also they use our system to track the fingers, and they can follow our tracking graphs. So they can identify how the fingers merge and split, and how the volume of fingers grow in space by using our system.
Right, thank you. Related to that, one of the obvious questions with an application paper, or a paper that tends towards the application, is whether or not it's generated publications in their domain as well as in the visualization. Has it got to that stage yet?
At first, why we publish in the visualization venue, because at first we have visualization researchers, so we want to publish it in our venue, and also we want to develop some new visualization techniques to help the domain scientists to achieve their goals, to analyze the fingers in space, and both in space and time. And actually we have a new tracking graphs, which is improve the previous tracking graphs to display
What
this.
I was actually asking was whether or not the domain scientists have got publications out of this in their domain.
No. They in their domain, actually they they were basically previously they are little studied this kind of geometric structures. They usually were analyze the fingers manually or by visual inspection. Actually, our work can extract the fingers automatically, which can make their works more efficient to analyze and identify the fingers.
And that implies that, given some time, there will be publications coming out of their domain, and that's always good to see.
Yeah, that's true. The domain scientists suggest us to have a kind of this paper in their domain.
Well, I heartily recommend it.
Yeah, thank you.
We're now 9 minutes behind, which is about where we were before. So I think we'll move on to the next talk, which I believe is being presented by Duong Huang, and it's titled Efficient and Flexible Hierarchical Data Layouts for a Unified Encoding of Scalar Field Precision and Resolution.
Hi, so I'll be talking about efficient and flexible data layouts for encoding scalar field precision and resolution. So the scientific data has been getting larger and larger thanks to advance in computing power in recent years. Volumes that measure in hundreds of gigabytes in size, such as the one shown here, is nowadays very common. If you want to study such volumes and do not have a very powerful workstation, then the next best option is probably to perform some kind of compression. There are two main compression approaches, reducing the data resolution or reducing its precision. It is interesting to note that so far there has not been much effort in studying how to combine these two forms of data reduction, but as we'll see in this talk, we can combine them to achieve significant data reduction. So let's try to categorize data reduction techniques in this 2D space of resolution and precision. Most compression techniques perform some kind of quantization, which reduces the data precision. Hence, each such technique produces one approximation that corresponds to one point in this space. Next, biplane embedded coders such as CFP can produce a progression in precision, where if we continue to decode, we obtain data approximations that are more and more accurate. On the other hand, resolution-based techniques such as Oct trees gives us progression in resolution, where approximations get finer and finer as we decode. JPEG 2000 is probably the first attempt at combining resolution and precision. It gives us a single progression curve in the precision resolution space. Finally, our data layout that we are presenting allows data reconstruction at any point in this 2D space, and therefore any progression curve is possible. So why do we care so much about allowing access to the whole precision resolution space? The first reason is that we can achieve better data quality by combining reduction in resolution and reduction in precision. If we reduce the data in either axis only, we are quite limited in the amount of data that we can reduce before the data quality becomes too low. For example, we can see banding artifacts if we go too low in precision, and pixelated artifacts if we go too low in resolution. In contrast, the last image here is of middle resolution and middle precision and is free from visual artifacts. More details can be found in our 2018 VIS paper. And the second reason why we want to allow access to the full resolution precision space is that sometimes we need resolution and some other times we need precision for the task at hand. Here we want to extract an ISO contour from a 2D function. On the top row, the function is rapidly varying, so more resolution is needed for a more accurate contour. On the bottom row, however, the function is much smoother, so more precision is needed instead. You can see this by comparing the contour in the second column with the one in the third column. For the top row, the third column is better than the second, while for the bottom row, the second column is better than the third. Given that sometimes approximation with more resolution are better and sometimes those with more precision are better, what we really want is a single data layout from which we can query the data at different resolution and precision levels, depending on the task at hand. So let's see how we can do that. First, let's get into a little bit more detail on what we mean by reducing resolution and reducing precision. Consider this 4x4 rate scale image and its pixel values in binary. We can obtain a 2x4 approximation to this image by retaining only half number of pixels in X and throwing away the rest of the pixels. Or we can also obtain a 4-bit approximation of this image by retaining the most significant 4 bits for each pixel, zeroing out the rest of the bits. And the technical term for this is quantization. In this case, we can say that we retain only the first 4-bit planes of the image. So given that in either case we know exactly which bits to retrieve, can we easily query the data at any resolution and precision levels? So the problem is, in practice, this reads happens not in units of individual bits, but rather in units of multiple bytes at a time for performance reason. So this is how bits are typically laid out on disk for the previous image in row measure order of the pixels. If we assume that this grids happens in blocks of 4 bytes, then for either the resolution or the precision case, even though we want only a subset of the bits, we have to perform 4 disk reads to get the bits that we want. And essentially we are reading the whole image from disk with these 4 reads. Of course, we can throw away the bits that we are not asking for, but this is obviously very wasteful. since if we already fetch the bits from disk, we might as well use them. Our solution to this problem is to arrange the bits and organize them into chunks such that each chunk does not span across the resolution levels or bit planes. Then, if we read from the disk in units of chunks, we can choose to only read bits that belong to certain resolution levels or bit planes. This way, we do not read bits that we do not need. But first, we have to associate each bit of the data with a bit plane and a resolution level. Let's see how we can associate each bit with a resolution level. We do so by constructing a tree where every node is associated with a grid point. In fact, the association is bijective, so every grid point is also associated with a tree node. In the paper, we give a formula to go from a grid point to the index of its corresponding node in the tree. That's why you see here we can number every tree node and a grid point accordingly. The nodes and grid points here are colored by the resolution level, and as we traverse the tree from the top down, we obtain finer and finer approximations of the original field. In fact, there are more than one way to construct such a tree. In the paper, we give a general formula that depends on a parameter d, which controls the branching factor of the tree. We have already seen the case where of d equals 2, where the resulting tree is analogous to a quad tree in 2D. D can also be 1, and the resulting tree is analogous to a graded tree, which can be seen on the right. In 3D, the formula also allows for d equals 3, producing a tree that is analogous to an octree. In 3D, d equals 3 is the most natural choice. However, it is totally possible to use d equals 1 or d equals 2 as well. We can actually extend our tree model to incorporate precision as well. To do so, we start by constructing a resolution tree, but only for the first bit plane. For the second bit plane, we add one child for each node of the first bit plane. Similarly, for the third bit plane, we add one child for each node of the second bit plane. Suppose there are only 3 bit planes, then our precision resolution tree is now completely constructed. With this tree, we can take a cut, which can simply be understood as taking a connected set of nodes that contains the root. Each cut corresponds to some approximation of the original field. For example, this cut here gives the approximation C that is low in resolution but high in precision, because we take only the first 2 resolution levels, but all the bit planes. On the other hand, this approximation B is low in precision and high in resolution, because in the cut we take all the resolution levels, but only the first bit plane. Although our tree model is complete, in practice, to arrive at an efficient data layout, there are a number of other concerns to be addressed. So in our data model, we introduced a few more abstractions to address these concerns. From left to right, we consider partitioning the data into bricks for random access, filtering, or transforming the data samples for high-quality data at coarse resolution levels, and finally compressing the transform coefficients in blocks. Of course, as mentioned before, the compressed bits are grouped into chunks and written to disk in units of chunks. With parameters such as the brick size, the filtering operator, the block size, the compression method, the chunk size, our data model is complete. We note that certain choices for these parameters recover known data layouts in the literature, such as the IDX file format or JPEG 2000. We found that we can achieve effective compression by using the linear B-spline wavelets for data filtering and ZFP as our encoder of choice to compress the wavelet coefficients. So those are our default parameter choices. Let's see how data reconstruction works in our framework. Assuming you have compressed the data and stored this 2D image on disk, to query from the data layout, in general, we have 2 knobs that are resolution and precision levels for each brick of the data. So the reddish image here indicates how refined each brick is. You may imagine that we have 2 such refinement maps, one for resolution and one for precision. Given the refinement maps, the data layout fetches only the relevant data chunks from disk and returns a corresponding approximation. There is another way that the data can be queried. When given a data budget, the data layout fetches chunks that minimize the root mean square error over the whole field and returns an approximation where each brick can be differently refined in resolution and precision, depending on the actual data. We can do this because in the wavelet domain there is a natural ordering of bits that minimizes the RMSE in a data agnostic way. So our data layout can be used purely as a compressor. So let's compare our compression performance of our method against the state-of-the-art compressors, namely SZ and T-Thresh. You can see that at the same compression ratio, here about 300x, our data quality is somewhere in between that of SZ and T-Thresh, and we're not very far behind T-Thresh. When comparing against ZFP, our method is able to push the compression ratio further while maintaining visual quality because we can leverage data reduction in resolution on top of the compression in precision done by ZFP. Here we compare our decode time and memory usage against those of SZ and T-Thresh. Looking at the vertical axis on the right, which is time, and the black curve, which plots the decode time, we see that our method is about 5 times faster than SZ and about 100 times faster than T-Thresh. Looking at the vertical axis on the left and the orange bars, which plots the memory usage for decoding, again our method uses orders of magnitude less memory compared to SZ and T-Thresh. Note that both vertical axes are in log scale. If we compare our decode time against CFP and plot that ratio against the data quality measured in peak signal to noise ratio, then we see that if we only consider the decoding at the finest resolution level, then the speed of our method is always within 20% that of ZFP, as indicated by the green curve. If our method is allowed to decode at low resolution levels, however, then for low and middle data quality, namely PSNR from 30 to 50, our method can achieve much better speed compared to ZFP because for these quality levels, our decoder can work at lower resolution levels. Here is an example of what you can do with our data layout. We revisit the 900 gigabytes volumes shown at the beginning of the talk. We show here 3 approximations of increasing resolution and precision, all obtained from the single data layout. They are of sizes 7 megabyte, 112 megabytes, and almost 1 gigabyte, obtained in 1 second, 2 seconds, and 85 seconds, respectively. You may imagine each of these approximations is useful in a different situation, depending on the hardware that you're using and the task that you have at hand. In conclusion, we have introduced a unified model that unifies precision and resolution in a single tree. We also introduced the family of data layouts that encode such trees, and classical encoding schemes are members of this family. With carefully chosen parameters for the family of layouts, we proposed an implementation that achieves competitive speed, memory usage, and compression ratios. And finally, our data layout allows decoding with different precision and resolution trade-offs for the needs of the application. Our code can be found on GitHub. The slides and paper preprint can be found by scanning this QR code. We thank these sources of funding for the project. Thank you for your attention.
Thank you very much for that talk, Duan. I noticed that with the exception of that last big data set, all of your examples were images in 2D. And so I have a slightly complex question for you. We had observed in previous work that there was a difference between volume rendering and isosurface extraction in terms of the quality of compression schemes. And it seemed to be related to integration, in which there is a relationship between the precision and the resolution. Have you observed anything similar?
So actually, I cannot say that I observed anything similar, but like you said, due to that integration, there can be differences in terms of result quality in the two cases. But this is something that we plan to look into in the future. So this is mainly just a data layout for you to query data at different resolution and precision per your needs. But how to use the data layout is another question. Like given the task, how much resolution do you query and how much precision you query for the task?
Well, the specific that I was thinking of is there's something called the Viscous covering theorem for integration, where the quality of the integration is related to how close your neighborhood is for covering your data set to a perfect sphere. And if you're integrating something which has a function value over your domain, then you're now in a domain one dimension higher. And so your neighborhoods you need to make sure that you don't distort them preferentially in one direction or the other. And of course, that's precisely the distinction between precision, which is the functional value, and resolution, which is the domain itself. So there's interesting connections there that I ran into with my student Brian Duffy. And I was just wondering if they popped up here.
A very interesting issue. I would like to discuss more with you later on about this.
I'm happy to do that. Just send me an email and we'll line up a discussion.
Yes.
Are there any other questions? It looks like somebody's typing a message, so we'll wait for a minute. I think that's all the questions that we're going to have. So I would like to thank all of the presenters for 6 very interesting talks, and hope to see you in person next year.
The mixture graph is a data structure for compressing, rendering, and querying segmented volumes. Biomedical segmentations have evolved from mere annotations to first-class modalities. The mixture graph stores the computations required to render such nominal data directly on the GPU, including pre-filtering and lighting. Segment distributions can be queried efficiently using regions of interest.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of 2 different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
We present our work on data visualization, a technique which helps facilitate understanding of physical measurements and quantities by providing visual experiences to users in virtual reality. This allows them to experience the ground truth of what the data is in reality, as compared to the abstract nature of conventional data visualization. We hope our work will spur new considerations into how immersive technologies can be used for visualizing information, and that you will find it interesting.
Exploring the emotions of students in classroom videos can help both teachers and parents know about students' learning status, and further help teachers improve teaching. However, it is a non-trivial task to analyze the emotion evolution of a group of people from classroom videos due to 3 major challenges. We propose a visualization system which integrates the model uncertainty and supports both collective and individual emotion analysis.
To interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. We create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation, which is especially well suited for the density-based visualizations shown here.
Blockchain has gained more attention and its applications are emerging. We collect 76 blockchain visualization tools and systematically classify them into 5 aspects: target blockchain, blockchain data, target audience, task domain, and visualization type. In the end, we look at open challenge in blockchain visualization.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TSNE projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, how can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TSNE, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
Many techniques can be used to render and visually explore large 3D line sets with transparency. However, all these techniques differ in several aspects such as runtime performance, memory consumption, and image quality. In this work, we provide an extensive comparison study to discuss the advantages and drawbacks of transparency rendering techniques for large line datasets.
TaxIMIS is an interactive visual analytics system to help tax officers identify suspicious tax evasion groups. The system integrates the traditional data mining algorithm and visual analytics techniques. 4 coordinate views are provided to support interactive exploration of tax evasion evidence. We demonstrate its usefulness through case studies using real-world test data and expert interviews.
Do you have a research question but aren't sure how to go about answering it? Are you interested in collaborating with psychologists but want to learn more about how they do research? Our paper presents a comprehensive toolkit of empirical methods organized across 4 categories to help you think about presenting visualizations as experimental stimuli in order to explore and measure how people perceive data. Check out our paper.
Hi everyone, I hope you're doing well. I'm Heikyu Park from Georgia